Okay. So, we will continue with application of rotating field theory of asymmetrical machines. Okay. And to recap, we have the equations for asymmetrical connections. Okay. And if it is a symmetrical machine, what we concluded was it will have a positive sequence impedance isn't it. We said if it is a symmetrical 3-phase machine, it will have a positive sequence impedance Z1 which will have ZL plus 3 times ZF1 plus ZB5 plus ZF7 etc. Okay, that we have done Z1. Then we also said that Z2 negative sequence I am just summing up what we have done earlier. Negative sequence impedance of a 3-phase symmetrical machine including space harmonic will be its leakage impedance plus 3 times ZB1, that is backward field, ZF5 and ZB7. You will see whatever was Z1, only thing that happens to the Z2 will be whatever was F in the Z1 will become B here, right. Forward field for positive sequence will become backward field like that. Then we have the 0 sequence impedance which will be again Z0 will consist of 3-phase system. What did we learn? ZL will be there plus 3 times ZF3 plus ZB3 plus ZF9 plus ZB9, all the triplen harmonics, isn't it. So, this is what we have learned. But if you take a symmetrical 2-phase machine, we found that the positive sequence impedance in that case will not be same as the Z1 here. So, if you call this as Z1 dash, we found out it will have ZL, the leakage impedance, plus twice ZF1 plus ZB3 plus ZF5 plus ZB7 etc. Okay. So, you will find a different combination, although the fundamental will be there. Okay. And if you have go to the negative sequence in the 2-phase system, that means I take a 2-phase symmetrical machine, find out the negative sequence impedance, means it is voltages are applied in negative sequence and we are taking all the space harmonics into account. It will have ZL plus twice ZB1 plus ZF3 plus ZB5 plus ZF7 etc. Okay. And here there is no 0 sequence. Okay. I hope these derivations we obtained from the rotating field theory. After getting the voltage equations, we apply symmetrical components and get these impedances. So, you will see that the sequence impedances will be a combination of leakage impedance plus the rotating field impedances. Okay.
Sir, what will be the 2-phase?
What will be the?
I don't know whether this symmetrical 2-phase machine is a 2-phase machine or
2-phase machine.
Symmetrical component of
2-phase machine, no. See, in a 3-phase machine you have 3-phase symmetrical components, in 2-phase machine you have 2-phase symmetrical components. So, if you have a 3-phase machine you will have ABC windings symmetrical and you will have V1, V2, V0. The sequence, if it is applied with positive sequence it will have Z1, negative sequence will have Z2, 0 sequence will have Z0.
Can't we define 3-phase symmetrical component with a 2-phase machine?
3-phase symmetrical component with a 2-phase machine. Okay. Now, you have AB, the 2-phase machine will have 2-phase symmetrical components, M-phase machine will have M-phase symmetrical components. Okay. So, that is
For the first single phase machine, we have done 3 phase and 2 phase both.
yeah, no, single phase machine we have not done 3 phase. Single phase machine, yeah, single phase machine can be you can have 2 phase, because single phase is non phase, it is an asymmetrical thing. Yeah, you can apply AB, then you see for example, we have always said the symmetrical component can be applied only if the machines are symmetrical and displaced by 2 pi by m, where m is the phases, right. Rotating field impedances, they are direct voltage and currents are there, therefore, there you can go for rotating field impedances, right. Therefore, this 2 phase, this will be the 2 phase symmetrical components and 2 phase windings. You can't have 3 phase, because symmetrical component will be only for as per the number of phases that you have. Okay. Now, your question is, if you have a single phase, okay, interesting. If I have a single phase winding, this is all I have. Okay. Now, what I did was, I said this can be considered as a 3 phase winding, ABC and BC absent. That is what we did. So, it is a 3 phase machine with 1 phase is present. So, we applied the 3 phase symmetrical component, because you take it as a 3 phase machine, or this is also equal to a 2 phase machine with B absent.
So, that is what I am asking.
Yeah, I have made, now what we are trying to say is, if there is a symmetrical machine, okay, this can be done with only 1 phase. Supposing I have 2 phases, what will you do? You can't make this to be equivalent to this and make something else absent. See, if one person is there, you can say all others have gone home, that only that person remains. Okay. So, this is not logical to do. You can even have m phase with m minus 1 phases absent. Okay. So, this is possible, right. Okay. Now, what we did for, as you are saying, if a single phase connection is there, we considered if you have a 3 phase case, that means with 2 phases open. I mean 3 windings are ABC is there, B and C open, or we took a 2 phase case with other 2 open. Okay. Then we derived, I think in several lectures earlier, that the impedance will be Z1 plus Z2 plus Z0 by 3, is not it? If we took only one winding, this was our equation. Okay. And in 2 phase case, we said it is equal to Z1 dash plus Z2 dash by 2, right. I think this we have derived. Okay. So, in one case we say we have these 3, Z1 by 3, Z2 by 3 and Z0 by 3. In the other case, we said it is Z1 by 2, or we say Z1 dash and Z2 dash because it is just taken. So, the Z has to be, now interestingly, if you substitute for this, we have got this Z1, Z2, Z0 from here for 3 phase and Z1 dash, Z2 dash for here for 2 phase, is not it? Okay. Then what will happen? If you substitute this, okay, Z1, Z2, Z0 from this, from those equations, and Z1 dash, Z2 dash from those equations which we have already obtained, earlier I have written. Okay. If you have these equation, if you substitute, what you will find here, you will have ZL plus ZF1 plus ZB1 plus ZF3 plus ZB3 plus ZF5 plus ZB5 ZF7 ZB7, and that is easy. see if you go here you will have ZL, you ZL, 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 if you add that by 3 will be ZL, then you sum up this will be 1 by 3 of this. So, it will have ZF1 is here, there is no ZF1 here or here, okay. Then you have ZB1 here, right, then you have ZF3 here, ZB3 here, ZF5 here, ZB5 here, ZF7 here, ZB7 here, ZF9 here, ZB9 here. So, you have all the odd harmonics are present when you connect on single phase, okay. Now, you have also got it should be same as Z1 dash plus Z2 dash by 2, okay. Now, that by 2 will be ZL, ZL will be ZL only, plus you have by 2 means this 2 will go. So, you have ZF1 here, ZB1 here, ZF3 here, ZB3 here, ZF5 here, ZB5 here, ZF7 here, ZB7 here, etc. Is it clear? Well, I think it is very important concept. So, you notice by this that the Z here, whether you take a 3 phase case with 2 open or a 2 phase case with 1 open, will have to give the same impedance Z, which will be, so Z1 plus Z2 plus Z0 by 3 should be equal to Z1 dash plus Z2 dash by 2, which is true because this all these terms are here, ZL, ZF1, ZB1, ZF3, ZB3, ZF5, ZB5, ZF7, ZB7, all odd harmonics are there, okay. So, you will have to sum up, you will have the single phase case. What will be the impedance? So, you will have ZF1, ZB1, ZF3, ZB3, okay, like this, is not it? ZF5, ZB5. So, this will be your Z. So, if you apply a voltage and it will pass a current, so that I will be equal to V by Z. So, if you have a single phase case and it considers all harmonics, right, is it okay? So, you can write, if you have a single phase motor, it will have all the harmonics and it will have, that means all fields are there, you know, this is due to forward field fundamental, this is due to backward field fundamental, this is due to third harmonic field, this is the forward third harmonic, backward third harmonic. So, it will all be because they are all inducing some voltages, say EF1, EB1, like that, because you know the air gap there are fields, it will induce voltage in those windings, I mean in that winding, okay. So, we have a net impedance which will have a leakage impedance ZL plus all these harmonics. Is it clear now? What will be connection diagram?
This is for single phase.
Yes. So, connection will be V1, it will be connection of 3 phase machine. If it is symmetrical, it will be only Z1 plus Z3, you know, we have seen, but if it is positive sequence, it will be something, negative sequence, it will be something, but if it is a unbalanced, it will have a combination of all. So, we have to take positive sequence impedance separately, negative sequence impedance separately, zero sequence impedance separately, or you can go through the actual rotating field thing. So, VA, VB, you have the impedance matrix, VA, VB, VC will be equal to ZAA, ZAB, ZBC, they will consist of these impedances. Okay. In 3 phase you can directly calculate or indirectly calculate through the transformation to symmetrical components. Okay. Is things clear up to now? I do not, you should, sometimes I get I am afraid that you appear to be blank. Okay. What I mean is a single phase motor, it will have leakage impedance plus all the impedances, which is, that is the starting point actually. We have come back to the same point, okay. And we again said that if it is only one winding is there, we have said it will be voltage will be leakage impedance plus all the forward and backward harmonics, and we said ZL plus ZFN plus ZBN, that is what we have done. So, with single machine, that is the impedances that we will get, and these are already defined earlier, that means ZFN, ZBN have been defined and we have done it earlier. So, these are the impedances if you have a single winding. Okay. This we have. So, we got back to the same point honestly. We started with this point with this and got back. Okay. So, ZF1, ZB1, ZFN, ZBN. Okay. So, we of course, we have already defined ZA, ZDIB, ZDSC, ZBA, ZCA. Okay. All those things we have already defined if you have multiple windings and all these impedance ZBB, ZBC, ZCB, ZCC, etc. Okay. Now, I want you to take a little effort. Now, what is this ZF and ZBN mean? What does it? If you go back, what is it? What do you understand now? Can you tell me what is this? What have you defined this as? ZFN is? What is my ZFN? Nth harmonic. So, we now what is this? We defined this impedance as the whatever is the voltage are due to the nth harmonic divided by the current which is a fundamental only. That is what we defined as ZFN, right. That means, we have said I pass a current, there is a forward rotating field and this EFN will be equal to 4.44, F is same and KWN into the series turns, the number of turns also will be different for nth harmonic Fn and the flux will be phi n. What is phi n? Is the flux per pole due to the nth harmonic. This is what we have defined. This is what EFN, of course, divided by the IS. Okay. And we also realize that this flux will have a rotor current effect also. This flux that is produced is the net air gap flux, not just due to the stator flux. Okay. Now, what it should contain? Okay, it should rotor reaction. If I ask you to write that one, okay, and this of course approximate circuit will be, it will have its magnetizing reactance by 2. You look at the equivalent circuit. So, this will be your ZFN. In parallel with, there should be JXLR, I would say N, because it may be the leakage reactance may be different. XMN is the magnetizing reactance corresponding to nth harmonic, okay, and this will be RR N. I say it may be same, but why I say there may be skin effect and other things. Rotor, that means how the rotor current, because the slip is different, isn't it? And then okay. Have you understood this?
So, why have we divided XLN by 2?
It should not be divided by
Yes, you have to think now. This definition of ZFN on a single phase motor, okay, will have whatever we did earlier, ZF, that has to be, because single phase motor is ZF, but in a single winding, what was our fundamental equation? See, if you look at a single phase motor, what was our equation? this is single winding, because we are now talking single winding only, not more than one winding. So, we always said RS, JXLS for fundamental, this is only with fundamental only. What did we say? This is XLR by 2, RR by 2S, okay, and JXM by 2. This is what we did, no? This will be JXM by 2. This was our first equation, right. So, there is this, and incidentally in the paper I referred, there is a mistake, 2 is missing.
Sir, but this whole thing is referred as ZF by 2 and ZB by 2.
Huh?
ZF by 2.
So this is ZF by 2 and ZB by 2.
Yeah, but in this definition of ZF, that by that 2 is not there incidentally. You see, the thing is with single winding, what the circuit we had? What is circuit we had? I am not putting ZF 1 by 2. It is a single winding, okay? Single phase connection, one winding, right. So, why I deliberately took this for further discussion was that you may get into a confusion when you refer to the rotating field, this thing, okay. I think we will I think when I take it further it should be clear now. So, this ZF1 will have a different connotation than the earlier ZF which we had defined, okay. I mean, I know that sometimes if you do a different approach, this is what it is, okay, right. So, I wanted you to be clear on this. So, what will be ZB? What will be ZBN? So, it will have J x m for nth harmonic by 2, then J x L r for nth harmonic, and it will be R r for nth harmonic divided by 2 minus okay. This is also important, ZBN. Now, sometimes sometimes they connect RC. What is this? Sometimes they connect it. What is this for? Core loss. Because even every harmonic, there may be a core loss component. Sometimes they do it. Okay. So, you can also put RC, right. Well, they also have some series impedances also associated harmonics. It will confuse you more. I am just deliberately avoiding that. Sometimes they have a additional leakage flux due to these harmonics, associated harmonic, which okay, and there will be stray losses and things like that. So, it is getting into more and more complicated aspects, but I think this much understanding at this stage is enough for you. Okay. Right. So, my new definition I would call definitely a new definition of say ZF1, ZB1. What will be ZF1 here? Will be XM by 2, XLR by 2, RR by 2S, is not it? ZF1. Then ZB1 will be same XM by 2, XLR by 2, RR by 2 into 2 minus S. Okay. Okay, so we had this right. Now, we have this with only fundamental field, we will okay. Now, I wanted to know what is slip for nth harmonic. What do you mean by Sn? That is also important, is not it? What is slip for fundamental? Okay. R 1 minus, no problem. R, what is n by ns? Will be 1 minus S 1. I say S 1 because fundamental. Fundamental field, this is what your normal synchronous speed is. What will be Sn for nth harmonic? What will be the slip? What do we define as slip is the difference between the actual air gap field minus the actual rotational speed, is not it? So, what will be this for nth harmonic? Huh? So, it will be ns by n minus n, speed does not change, it is rotating at the same speed for this, divide by. So, this will be Sn, okay. So, this will be 1 minus n by n into n by ns. What is n by ns we have defined as 1 minus S 1, no, this will be 1 minus n into 1 minus S 1, is it right? This will be 1 minus n plus n into S 1, okay. So, we can get for the nth harmonic Sn will be equal to 1 minus n plus n times S 1, right. For example, what will be S 3? What will be S 3? 3 S 1 minus 2, okay. S 5, 5 S 1 minus 4, okay. Now, you will notice, supposing S is let us say S 1 is point say 0.5, what will be this? So, it will be let us say 3 into this. So, 0.15 minus 2, this may be 0.25, is it? Is it right? Okay. Now, what you notice is while this slip is low, it is almost like, so rotor currents will have altogether different values. So, if this is slip frequency for the fundamental, for this will be very small, okay. Then what will be this? This is almost like nearly 2, this is nearly 4. So, rotor currents will have 100 cycles, maybe 200 cycles. So, there will be high frequency currents in the rotor because of the harmonic fields. Okay. If harmonic fields are absent, you have no problem. Okay. Unfortunately, in actual machine they will be present, because in engineering you go on doing assumptions to make your analysis simpler, but in actual engineering systems all of them will be present. Okay. So, one of the assumption of engineering system is that all systems are perfectly imperfect or imperfectly perfect, is it right? All engineering systems are imperfectly perfect or perfectly imperfect, okay, whichever way you look at it. Okay. So, but a scientist will make lot of easy assumptions, and he will thinks, scientist thinks everything works as per his law, but a nature is such that nature will defy our laws of science invariably. So, you create new laws, right. Okay, now, with only fundamental one we have the standard equivalent circuit, is not it? So, we apply a voltage V with only fundamental, okay, then RS, JXLS, JXLR by 2, RR by 2S, RR by 2 into 2 minus S, XLR by 2, JXM by 2, JXM by 2. This you have already seen, okay. And this is as per our new definition, this is ZF1, this is ZB1, okay, and this is was your ZL, right. This is what was defined. Now, I am specifically saying because of confusion you may have with the earlier one we defined ZF1 as twice this, that is all, right. Okay. Now, so we know now that you have a powerful tool in your hand using rotating field concepts. If you have a 3-phase machine, if it become asymmetrical, what I mean asymmetrical is supposing interturn faults are there, that means they are 120 degrees arranged, but turns are different, okay. You can analyze that also without any problem. So, but then what happens is ZJL will be ZBL by KB square, ZCL by KB square, because if the number of turns are different, leakage reactances are proportional to square of number of turns. Usually R is R and XL are normally proportional to n square, right. Resistance is proportional to n square and leakage reactance is proportional to n square. So, if you refer them, they will all have that. So, you can always write ZJA, ZJA by and ZJB by KB, ZJC by KC and will be ZBB by KB square, etc. Okay. Now, all these terms are, you can define all these quantities, okay. I think we need not to waste time because you have the equations, substitute this, but the angle will be theta B is 120, theta B will be 240, theta C is 120, that is all, okay. And you can, therefore, you can always have VA, VB, VC in terms of the constants A, B, C. Only thing is that will have the terms KB, KC, because KB is not equal to 1 and Kc is not equal to 1, that is the only difference here in a 3-phase asymmetrical machine, okay. Then you can refer them to the same reference terms. So, you can have VA dash, VB dash, VC dash, which comes to be the same as the standard equations. So, VA dash is VA and IA dash IA, VB dash is VB by KB, VC dash equal to VC by KC, and basically referring is done, okay. Since we have done it several times, I thought let us not elaborate. So, all you do is if you want to make your equations manageable, you refer all the parameters, voltages and currents into the referral winding terms, okay. So, these equations are so referred equations, they have been referred to an equivalent symmetrical 3-phase machine. When you refer them, it will almost look like a symmetrical machine, but impedances are different. So, remaining calculations are done in the same way as in the case of symmetrical 3-phase machine, okay. So, this is how you analyze an asymmetrical 3-phase machine. Asymmetry is only by number of turns, okay. Now, same thing you can do for 2-phase also. You have 2-phase asymmetrical machine, that means they are at 90 degrees, but carrying different turns, okay. So, you have ZJL, ZB equal to ZBL by KB square, that will be ZL, okay, and you can have ZAA, ZAB by KB, ZBB by KB square, they will all be same. So, you have the parameters A dash and B dash, which will be impedances in terms of ZF and ZBs, okay. I am again not elaborating much because they are simple simplification of the original equations which you have got. So, you can have V A dash V B dash you can write in terms of the currents I A dash I B dash, the dash is only for two phase system. So, you can have an impedance parameter. So, when once you know V A V B you can find I A I B, is not it, because you know all these parameters, right. So, you have V A dash V B dash, you can refer them all to the A phase terms. Okay. Now, in practice what are the problems? Okay. In practical applications, you have a starting performance of single phase motor. This is one issue you have, where if you are given a single phase motor with two windings, you must estimate the torque at starting, currents at starting, where two windings are there. Okay. Then you have the split phase winding method of starting. Okay. Many times what happens is even three phase machines are started with split winding. Okay. You have a part winding starting of machines. In a three phase machine, part winding starting, then you have a single phase machine with asymmetrical two phase machine as a asymmetrical two phase. These are practical cases. Okay. You are given a three phase motor, you do a turns, there are tapped windings. Okay. So, when tapping windings is one thing, or if you do a variac type of thing, then you have the interturn faults in a three phase windings. We mentioned interturn fault is after it works for a long time may be heating. So, any of the windings may have a short circuit of certain turns, this is called interturn faults. And you have the analysis of capacitor motors, this is also another asymmetrical case. Okay. That is the two windings asymmetrical, but having capacitor. And how do you choose the capacitor? I give you a motor, you have to fix the capacitor. So, what value you choose? What is the criteria for choosing the capacitor? It should give a good starting torque, is not it? So, a capacitor which gives a good starting torque you have to choose, but that capacitor will not give you a good running torque. So, you have to find a good running capacitor. Okay. So, a person a capacitor which is good at starting is not good at running, just like a person if you want somebody who should be a good sportsman as well as good academic. So, you can't have, suppose an institute want to have, you can't have the same person to do both. So, they may have to maybe hire one sportsman, hire another academic maybe. Okay. So, you must have one good starting and good running capacitor. Okay. Then you may think of variation of capacitor of best performance throughout. I may like to vary the capacitor, right. So, this is also one of the practical problems that you face. Okay. Now, okay, we have already done this earlier in some other method. You have a two phase machine, we call it as auxiliary winding and main winding, is not it? Okay. This we have analyzed it earlier, right. This is a practical case, squirrel cage rotor, and the connection is main winding is the reference winding, this is the reference winding, and auxiliary winding which will lead by 90 degrees. Okay. This is a practical case that you will always be confronted with. Now, how do you, and we have seen, now can we, now why not we analyze through our rotating field theory now, and you write the rotating field impedances. Rotating field impedances will be ZMM will be the ZLM, the leakage, plus ZFN plus ZBN, is not it, reference winding. Okay. And ZAA, that is the self impedance of the A winding, ZAA, will be again its own impedance ZL A plus A square, because number of turns is, so we have take NA by NM is the, this is what we have said, it has A time auxiliary auxiliary winding will have N times the turns of the main winding, A times. Okay. Now, an MA, that is the mutual impedance between M and A, will be A times ZFN e to the power of minus Jn theta B, that is minus Jn into theta B is now pi by 2, it is leading, okay, pi by 2, plus ZBN plus Jn theta B, that is plus Jn pi by 2, is okay, but it will have A times this. So, ZAM will be the complex conjugate of this, that will be A ZFN e to the power of Jn pi by 2 is a minus, it is plus ZBN e to the power of Jn pi by 2. So, this is our general impedances. Okay. Now, supposing we only take the fundamental field, let us say as our first approximation only fundamental field. Okay. Then what fundamental field means, you put n equal to 1 only, neglect all other n's, is not it, all higher harmonics you neglect. Okay. So, ZMM will be ZLM plus ZF1 plus ZB1, is not it, sorry, that will be your ZAA, sorry, ZMM. ZAA will be ZLA plus A square into ZF1 plus ZB1. Okay. And ZMA, that is the mutual between impedance, will be A times ZF1 e to the power of minus j, n is 1, minus j pi by 2, and ZB1 e to the power of j pi plus j pi by 2. Okay. And ZAM will be complex conjugate of this, A ZF1 e to the power of j pi by 2 and ZB1 e to the power of minus j pi by 2. Is it okay? All I have just substituted, I have neglected all harmonics. So, we have a two phase asymmetrical machine with different number of turns, okay, and displaced by 90 degrees. Then what will be, so you can easily write V M V A will be equal to ZMM, ZAMA, ZAM, ZAA of IM and IA. I think there is no problem here. Okay. So, if you substitute now, we have V M will be ZAA, which we say ZLM plus ZF1 plus ZB1 into IM plus ZMA is, we know what is ZMA, which is e to the power of minus j pi by 2 is what? Minus j, isn't it? Minus j, because this will be minus JA ZF1 plus JA ZB1. Okay. So, you can substitute this plus minus JA ZF1 plus JA ZB1 into IA, and VA will be ZLA plus Z A square ZF1 plus A square ZB1 into IA plus JA ZF1 minus JA ZB1 into IM, is not it? I only substituted that. Okay. Now, what we want to do is you refer them to the, so you write refer to main winding. That means you have V A dash will be V A by A, I A dash will be A times I A, and Z A dash will be Z A by A square. This we have done, isn't it? Refer the auxiliary winding to the main winding turns. Okay. Then you also have, next is you have done this, refer voltage equations to this. Then what you do is transform as, you put them as VSF, VSB. We have done that earlier. Okay. We said VSF is half of Vm minus J Va dash, this will be half of Vm plus J Va dash. Okay. And similarly for ISF, ISB. Okay. So, I want you to bring out this in the next class. What will be VSF, VSB in terms of what should it contain? I want all of you to do it. So, it is an assignment everybody should do. Okay. So, next class all of you should bring this assignment. Okay. And then you must try to get, you have done this earlier. We have this VSF, VSB, okay. Then this will be ZL, and you find out what is this, find out what is this, and you find out what is this, okay, after the derivation. Because when you have that 2 by 2 matrix, you can easily write the loop equation, and this will be ISF and this will be ISB. So, this will be the one you have to derive and bring the solution in the next class. Okay. So, we will close it here, we will ensure and now you can see what is the new ZF and what is the old ZF which we had defined. Okay. We will close it here.